In this video, we're going to be talking about how a computer compiles program code. We're going to be reviewing the lexical, syntax, code generation, and optimization stages of a compiler. So let's talk about the steps in compiling program code. Now, we have that keyword compiling, which means the computer is going to be using a compiler, and we're going to get those points on the exam. So that's why we're reviewing today. And the 4 steps are the lexical analysis, the syntax analysis stage, code generation, and part of code generation is the code optimization. So let's review these briefly so we can get more comfortable, because Cambridge loves to ask about this on an exam. So the lexical analysis stage. In a compiler, a lexicon is a set of terms known as keywords or reserved words that the compiler can understand. The lexical analysis section of a compiler is to convert the incoming source code into binary code or into machine code. Tokens are created. Now, tokenization is when the compiler or the tokenizer or lexer divides the input stream into individual tokens. It then identifies the token type and passes the token to the next step in the compiler. What the heck does that all mean? Because we can read it, but if we can't understand it, we're not gonna be able to remember that at all. So let's take a look at this, putting it in the context with an exam question. So this would be a question on the, could be a question on the exam. They like to ask questions like this. And when you see this, you should be thinking, my heavens, this is gonna be free points they're giving me. The compilation process has a number of stages. We just said that. They're telling us something we already know. The first stage is lexical analysis. We know that too. I wish they would have asked us, because we know that and we could have got more points. Anyway, a compiler uses a keyword table and a symbol table. And this is what we mean by creating tokens. It looks at each individual word or symbol or keyword, and it ties it to a token. Part of the keyword table is shown below. Tokens for keywords are shown in hexadecimal. That's going to be important momentarily. All of the keyword tokens are in the range 0025F. So that's what we have here. Entries in the symbol table are allocated tokens. These values start from 60, and they keep saying hexadecimal, and that is important. They're trying to point something out, which we'll get to momentarily. So these values start from 60. Here we have some code, start. That is something that we created. That is not in the token table. The computer does not recognize start as a key word. Number, that is a variable that we've created. It is not already in the token table, so we have to put these in the symbol table because they are symbols. And here's our symbol table, and we're going to fill it out. But to fill this out, we're going to need our code, and we're also going to need the existing token table. So we have the keywords. Keywords are words that the program recognizes, the compiler recognizes. The symbol are things that the compiler does not recognize, that we create, and we have to go in order, token by token or word by word in our program. So we have start. Start is not a recognized word by the compiler. I look in my keyword table, I don't see start. It told me that it starts from 60, so I put in start, I put 60. Now, is start gonna have the same value all the time? It could, but it may not. So we're gonna put that down as a variable. I look for the arrow. The arrow is recognized by the compiler. So I don't need to put that in the symbol table because the arrow, the assignment operator, is a key word. And then I have 1. 1, the compiler doesn't recognize that, so we put that into our symbol table, which is a 1. The previous value was at 60, so now we're going down to 61, and that is going to be constant. There is no instance where 1 doesn't equal 1. There is no instance where that happens, so it's always going to have a constant value. I keep going. I look at input. Input, that is recognized by the compiler. I have number. Number is not recognized by the compiler, so I need to add that to my symbol table. I add number. Well, remember, these values started from 60. We've already done 60. We've already done 61. We need to point to a different address on the RAM, which is going to be 62. And number, is that always going to be constant? No, it's not. It's going to be a variable. And you'll start to notice right away when you have these words, most of the time, they're going to be variable. When you have a number, they're going to be constant. Now, we got to keep going. These comments are removed. So now we look for 4 is recognized by the compiler. There it is, 4E. Counter. Well, counter is not recognized by the compiler, so I need to add counter. That's going to have a value of 63, the address, and counter is going to be a variable. It's not always going to be the same operation. I have arrow. Arrow recognized by the token table. It's a keyword. Start. I've already identified start, so I don't need to do it again. 2, TO. That is already identified. 12. 12 is not inside my keyword table, so I need to add it as a symbol. So I add 12. The value is going to be 64, and in every instance, 12 will equal 12. And all these others have already been identified, so we just picked up some easy points. So now what we need to do is the output from the lexical analysis stage is stored in the following table. They give us a table here, and this can look overwhelming. Super easy. Each cell stores one byte of the output. Complete the output from the lexical analysis stage. Not a problem, because all we have to do is do what the compiler does. We're going to take these keywords, we're going to convert them to their tokens, we're going to take our code, and we need our symbol table that we just created. So here we go. We start with start. Start, value of 60. That's where they got the 60 from. Arrow, 01. The next one is 1. Where's 1? 1 is in 61. Then I need to input. Where's input? That's token 51. Input what? Input number. Number is on my symbol table, 62. Then I ignore the slashes because those are comments. I look for 4, F-O-R. That is in 4E. Then I'm looking for counter. Where's counter? Right here, 63. Then we look for the arrow, 0, 1. Now you must write 0, 1. Why do you have to write 0, 1? Can you just write the number 1? No, you cannot, because it is in hexadecimal, and they said that multiple times. 0, 1 has a different value than 0, 1 in hexadecimal is different than just 1. Now, you can argue when you convert it to binary, it comes out the same, and yes, that is true, but they want the hexadecimal characters, so we have to write 0, 1. Now, where are we at? We're at the arrow. Oh, we're looking for start. Start was identified by 60. We look for TO. TO is in the symbol table, or the keyword table, excuse me, that is 50. And then I look for 12. 12 is in my symbol table. We put it at 64. Now, it's very important that you put these in order. You cannot say, oh, well, I forgot number and I put counter first. I'll just put number after counter. You cannot do that because the compiler, when it's going through this code, it looks at each individual label and makes a token for it. If it's a keyword, it makes a token for it. If it is a symbol, it makes a token for it. And because it goes word by word, number shows up before counter does. So yes, these must be in order. So we're at 64, which is 12. I move to the next part, output, which is 52. Output what? Number. Number was in 62. This asterisk, which is in 2. And then I'm looking for counter. Counter is in 63. And then I'm looking for the last one in 4, which is in my keyword table, and that is 53. And just like that, we picked up all the points for the lexical analysis stage. So here's an example. This would be time equals 5 plus 3. Time is an identifier, meaning it's a variable. Equal is an assignment operation. 5 is a number. Plus is an addition operation. 3 is a number. So that's another example. But once the table is complete, meaning all the source code is tokenized, is ready for the next stage, which is syntax analysis, which is also known as parsing. It creates a parse tree, which checks the grammar rules. So it analyzes the syntax of statements to ensure they conform to the rules of grammar, which is why we call it syntax. Now, many languages want to see an end-of-line marker. In Java, for instance, they want to see when you're done, time to put a semicolon. That's the end of the line marker. Another example, we need to end if at the end of an if statement. It needs to know what it ends. The next, we need that at the end of a for loop to know that it has been closed. Now, if it's missing, like the semicolon, the end if, the next, whatever it may be, syntax analysis adds an error to the comment section of the compiler. And this is called an error report. If you've ever compiled your program and it says errors were found, that was done by syntax analysis. Now, there are two parts of syntax analysis, and in stage 2, the syntax analysis becomes semantic analysis. It's important to understand that semantic analysis is still under syntax analysis. Semantic analysis makes sense of the relationship between the tokens. So in the lexical analysis, we make all those tokens. Semantic analysis makes sense of the relationship between them. After the semantic analysis, it's time for the next step in the compiler. So let's go ahead and summarize the syntax analysis stage. We're not going to do a Cambridge test question because literally they will ask you, what does the syntax analysis stage do? There's nothing to fill out. They're just going to ask you, what does it do? So what does it do? It constructs a parse tree. This is known as parsing. Now, they will count that as 1 point. If you say it constructs a parse tree known as parsing, that's going to be 1 point. Usually, they're going to ask you for 2 things if it shows up on the exam. It checks the table of tokens to make sure grammar rules are followed. And the last thing it does is it produces an error report. Because we said if a label has not been tokenized, meaning it's not recognized, there's going to be an error report. It's looking for that end if, the next, looking for that semicolon. If it's not there, it's going to produce an error report. So on to the next, which is code generation, also broken up into 2 parts. So after syntax, it's time for code generation. It creates object code. So what is object code? It's using what has been formed in the lexical and syntax analysis stage to make machine code, which is your binary code. So what happens when it's actually doing this? Well, it reserves memory and opens memory locations on the RAM for the variables that are used in our source code. Now, it doesn't identify the variables. We already did that back in the lexical analysis stage. It works out relative addresses for jumping around the program. This is when you call procedures, functions, methods, or specific lines in a program. Let's take a look at this example. So if x equals 1, then go to next step. So it jumps down here to this label, next step. And there could be lots of lines of code in between this, but the code generator knows the relative address of the label called next step and adjusts the if x equals 1 statement machine code, which will jump to it. So that's part of the code generation responsibilities. It reserves memory and opens memory locations, and then it works out relative addresses. But there's something else that it does during this code generation stage, which is optimization. We'll take a look at this example here in a minute. So after creating machine code, the code optimization stage will look for ways to reduce the code or make it operate faster. This means it will do the best that it can, but this means it may make it more efficient than what you have made it. The code generator optimizes the code it can the best that it can. This means producing code that is fast and efficient as possible. It will delete and remove redundant code or code that will not be efficient. Look at this example on the right. So first it would be x equals y plus 3. Then we take x and we put it in b. Well, I could just make x up here, b equals y plus 3. But then it says b equals c. Well, I don't need b, I don't need x. What the optimization stage does is it gets rid of b and x and it rewrites it as c equals y plus 3. So b and x variables are not even allocated memory because they are not needed. This saves space in the memory. The machine code will simply represent c equals y plus 3. And this is what makes some compilers better than others. Now with optimization, you can tell the compiler to optimize for memory or speed, but unfortunately you can't tell it to do both. On the exam, it'll ask you what, it will say the code has been optimized for memory. What is one other way it could be optimized for? Well, it's not what is one other way. There is only one other way, and that is for speed. They could also ask you, if it's been optimized for speed, what is one other way it could be optimized? Well, there is only one other way. If it's been optimized for speed, the other way it could be optimized is for memory, but it cannot do both of these. I hope you found this video helpful. If you did, please give it a thumbs up and subscribe to help our channel grow. If you have a comment, post one down below. We'll see you guys in the next video.